Hello, everyone, and welcome to the VaNTAGe seminar. Today, we're starting a new series of talks on the fundamental group of curves and their arithmetic applications. And we're very happy today to have Romyar Sharifi, who will be talking about arithmetic through the geometry of locally symmetric spaces. And Romyar, is it all right if we record this talk?
Yes.
Oh, wonderful. And everyone, feel free to ask questions during the talk. Romyar, please go ahead.
Okay, thanks very much for inviting me. I guess my talk, well, there's no fundamental groups in my talk, so it may fit in least with the theme, but let's see, there are definitely some connections. In fact, it was through fundamental groups that I came to, of P1 minus 3 points that I came to studying this. So let's see. Okay, so I pre-wrote here the philosophy. So the idea here that I want to explore is that the geometry and topology of modular curves tells you something about the arithmetic of cyclotomic fields. And particularly when the point is that it's sort of working near the cusps, in some ways you get some sort of equivalent information. And okay, and what mediates between the two sides is Eisenstein series. So most of the talk today will be, to explain connections in this correspondence. And my program more generally, as the title of the talk indicates, is, a desire to understand these connections for in more general settings of locally symmetric spaces or arithmetic of Shimura varieties and such, Stelmer groups. Okay, so let me just review some, some number theory. So, the modular curve y1 of n can be viewed as a scheme over spec of z1 over n. And there we can think of it as being like let's say n's at least 3, or I mean, maybe I'll just take n to be at least 4 for, okay. So it's the fine moduli space. So it's with points for a z1 over s scheme, z1 over n scheme. The sort of equivalence classes of, or isomorphism classes of pairs where E is an elliptic curve over S, and P is a point of order n, which, to make sense of this, you can think of this as a map from the constant scheme to an injective map morphism to the like n torsion on the elliptic curve, mod sort of isomorphism. So the S points are these pairs of elliptic curves and a point of order n. Its C points is, the more classical object, which is the complex upper half plane modulo so this has an action of SL2Z in particular, and there's a congruent subgroup gamma 1 of n inside it, where, so here, what is the correspondence, right? I guess a point tau in H, right, gives you a pair, which is like C mod the lattice Z plus Z tau inside C, and then the 1.1 over n. So that sort of gives you this moduli interpretation. And let's see, what's the group gamma 1 of n? Gamma 1 of n is the matrices A, B, C, D in SL2Z with bottom row sort of 0, 1 mod n. So convert to 0, 1 mod n z squared. Okay, okay. And the modular curve has a compactification, right, which over C is given by adding in the cusps. So x1n the sort of minimal compactification. Well, so it's C points are just you extend by the cusp. So Mobius transformations act on the upper half plane. They also act on Q union infinity. And then we can take the quotient by the action of gamma 1n, and that is the compactification at C. There's also a moduli interpretation where you replace, elliptic curves with generalized elliptic curves. And in particular, so this is also defined over Z1 over n. The cusp at infinity, so the infinity gives you a point in P1 of Q. So infinity is defined, it's not a Z1 over n point, but it's defined over back of Z 1 over n and mu n. And I guess you could take the part fixed by complex conjugation, the maximal totally real subring. Okay. So in other words, infinity is a point, so it's a map from spec of this ring to x1 of n. And the key point about infinity is you see already here we have sort of a cyclotomic field or a cyclotomic n integer ring appearing. So infinity, the point I want to make is that it relates in the above sense, the geometry of x1n or y1n to the arithmetic of q mu n. We'll see more about how that goes shortly. Okay, so let me now say something about Eisenstein series. Okay, so if we have a character of Z mod n Z cross, and let me assume it's sort of primitive. In other words, it doesn't factor through any Z mod m Z cross for m dividing n and not n. And let's also suppose it's even, so it takes -1 to 1. And then we can extend by 0 to a Dirichlet character, right? This gives me a Dirichlet character from Z mod nz to Q bar, extending by 0 at the points not prime to n. There are the numbers. Okay, and so then we have the Eisenstein series of weight 2, sort of classical Eisenstein series for the character chi. Often there's a pair of characters involved, but I'm only considering this sort. So it's some generalized Bernoulli number over -4 times plus some, so I'm giving its Fourier expansion, some n equal 1 to infinity, d dividing n. So this is some function on the complex upper half plane where here q is, what did I do? Oh, okay. Q is e to the 2 pi I z. Okay. And okay, and so this is a weight to level n, and it has Nebentypus or character chi modular form. Okay, and it's an eigenform for the action of all Hecke operators. So in particular, I mean, this can be read off from the coefficients, but they're diamond operators for d and z mod nz cross, and they act via the character because it's character chi. So t is prime to n. And then there's the Lth Hecke operator acts as the Lth Fourier coefficient, so that's 1 plus L chi L. But notice I just said that diamond operator L acts as chi L, so I could just write it this way. So if L is prime and does not divide n, and then we usually call that, the Hecke operator UL if L divides n. So, and then, so in that case, we have just the operators x is 1, okay, because we've extended by 0. And so, okay, so now let me suppose that P is an odd prime. Sometimes I may need it to be at least 5, but for now, just some prime. And we have, Hecke algebras. They're Hecke algebras. Acting on weight to level n modular / cusp forms, respectively, with ZP coefficients. Okay, so what's a modular form with ZP coefficients? You can think of it as a homomorphism from the Hecke algebra to ZP, and which then determines the Fourier coefficients of the modular form. Or if you take a modular form, it happens to have Z coefficients, and you just, so you take the set of all modular forms with Z coefficients in its Fourier expansion, and you tensor that with ZP, then you get modular forms with ZP coefficients. So this is a ZP, it's a ZP algebra, these two algebras. The first is of modular forms, and the second is of cusp forms. And so inside these Hecke algebras, either one of them, we have I in these Hecke algebra, the Eisenstein ideal. And I'll just take it to be generated by TL minus 1 minus L diamond operator L for L prime not dividing n, and UL minus 1 for L prime dividing n. Okay. So this is a Hecke algebra that sort of sees all characters at once, because I haven't actually put in that the diamond operator should act as in a particular way. But since I want to deal with primitive characters, I'm going to have to do that sometimes. Okay, so suppose, I have a module over the group ring of Z mod n Z cross. So imagine Z mod n Z cross could be acting as diamond operators, right? Or it could be acting as Galois elements for the Galois group of Q mu n over Q, which is isomorphic to Z mod n Z cross. So if I have a module for the group ring, then we can let m chi be the sort of maximal quotient of M on which, well, okay, we have to make sense of what this means, but there's a way to make sense on which Z mod n Z cross acts through chi. So it makes sense as a quotient. If chi is ordered to if n is prime to, if phi of n, the order of Z mod n Z cross is prime to P, then this is just a direct summand. And then this is a module, this is then a module over O chi, which is the ZP algebra of values of chi, which is a quotient of this ring. Okay. So there's a theorem. I'll attribute it. It's not directly written in Maser-Wiles, and Wiles proves something sort of more general, which implies this. And then there's also it's also sort of treated by Skinner-Wiles, Ota, Lafferty. But I think Maser-Wiles is enough really for this. That if I look at the okay, so let me make one point. So if we take big H mod I, this thing is actually just, let me look at the chi part of it. This thing is just actually O chi. Okay, and the map is TL goes to 1 plus L chi of L, and this is a ring homomorphism because to say a homomorphism from the Hecke algebra to a ring, which is a modular form. But a homomorphism from a Hecke algebra to a ring, which is a ring homomorphism, is a is a eigenform, and UL goes to 1. Okay, so that's the map. But because so this is coming from the Eisenstein series, right? This corresponds to G2 chi. But because the Eisenstein series isn't a cusp form, this doesn't give you you don't have a homomorphism from the cuspidal Heck algebra. So this is the modular Heck algebra, and this is the cuspidal Heck full modular from the just acting on cusp forms to OCHI. Rather, you have a homomorphism to a quotient. And what quotient do you have? Well, the point is here I have this generalized Bernoulli number. So this B2 chi is some element of OCHI actually. And it's, you know, it's congruent. Actually, let's say chi were like well, I'll go back like omega to the k minus 2, where omega is like a type Miller character or something, then this thing is congruent mod p to the kth Bernoulli number, which is some like number in Q. But you know, for k not 0 mod p minus 1, it's actually integral at p, and so you can reduce it mod p, or I mean, you can talk about whether p divides it, and p divides it if and only if there's a congruence between this Eisenstein series and a cusp form. And the basic point is that somehow the size of the Hecke algebra mod Eisenstein ideal, the cuspidal one, is telling you how many congruences you have. So the theorem of, and I'll say more about this in a second, theorem of Mazur-Wiles and Wiles that they proved as a consequence of the Iwasawa main conjecture is that this is, it can actually be proven without proving the main conjecture first, but it's like this. Okay, so the Bernoulli, once we reduce mod the Bernoulli number, then we can have a homomorphism. So we essentially have a modular form, a cuspidal modular form, eigenform, valued in this like finite ring. And that's the reduction of the Eisenstein series mod B2 chi. Okay, so this says G2 chi mod B2 chi. So we get rid of the constant coefficient is the reduction of cuspidal, and then you can actually see it lifts. So it doesn't quite say this, but cuspidal eigenform. Okay. So so the Eisenstein ideal measures congruences between G2 chi and cusp forms. Okay, I want to say another thing about the Eisenstein ideal, because I mentioned this cusp at infinity as somehow being important. So if we look at the sort of the chi part of the Hecke algebra, the part acting on modular forms with chi coefficients, sorry, no, with Nabin type is chi. So the Eisenstein ideal in this chi part of H is in fact the annihilator of chi in the chi part, the chi quotient of the ZP span of the cusps. So thinking of cusps as, you know, divisors, spans of ZP span of cusps in the divisor group. So we have Hecke algebras act on divisors as correspondences on the modular curve. Actually as dual correspondences is what I'm using here. And so we can look at the span of the cusp. The Hecke algebra acts. I take the maximal part on which diamond operators act through chi. I need that just because I need to look at the primitive part. And then the annihilator of infinity is exactly this Eisenstein ideal. So sort of in that way, that's why in the sort of initial philosophy, I said it could be either like geometry near infinity or sort of geometry modulo Eisenstein ideal. And now I want to talk a little bit more about modulo Eisenstein ideal. So this is sort of an idea that dates back to Ribbit. So if I have a new form, say its Q expansion is this, so it's a cusp form. This has algebraic coefficients, so we can think of them. Q bar as by some p-adic embedding as being in QP bar. And then the coefficients generate some finite ZP algebra, so generate finite rank ZP algebra, in fact, OF. And so in the sort of way I was saying, we get a homomorphism from the cuspidal Hecke algebra to the OF via, TL goes to AL, or TN goes to, I'll just write them all as TN, right? Like the nth Hecke operator goes to the nth Fourier coefficient. So this is a ring homomorphism. Okay, and now, okay, so this H now acts on the Tau cohomology. You can think of this in terms of Jacobians, but I want to write it as a Tau cohomology over Q bar of, let's say, ZP1 coefficients via, again, not the usual action, but sort of the dual action, which is better for compatibility with change in level via trace maps. Okay, and then we can consider TF mod this ideal, or sorry, T, which is T mod this ideal. The ideal attached to the cusp form. This is not the Eisenstein ideal, right? So for this IF, because F is actually a cusp form, we get a map to something which is, not torsion over ZP, where for the actual Eisenstein ideal, because it's a cusp form, we only get a map to something which is sort of finite. Okay. So this is a lattice in VF, which is TF tensor QP, which is the Galois representation attached to F. So the two-dimensional Galois representation attached to F. I guess in this case, it'll be two-dimensional over like the OF tensor QP. So the quotient field of OF. Okay. So the p-adic. So that's how you construct the p-adic Galois representation of a weight 2 cusp form. Now suppose that my F was congruent to this Eisenstein series. So suppose that F is congruent to G2 chi mod the, say, maximal ideal in OF, which is a prime over P. This is right, so, or the prime over P. So, okay, and so, in other words, you can think of this more as just like basically like they're congruent mod the Bernoulli mod prime dividing the Bernoulli number in this case. Okay, then the point is that the maximal ideals of, let's say, H chi containing either IF or the image of IH chi or whatever, coincide. They're now the same. And so if you, instead of like reducing mod this IF, you localize at this maximal ideal. Let me call this thing M just for now. Then let's see. T M sort of contains, as a quotient, I guess, the info of all Galois representations of cusp forms mod P at once. So it's convenient in that way, because how do you know there's like a unique cusp form that's congruent to an Eisenstein series mod P? Maybe there are, I mean, not even Galois conjugate, but maybe there are many. And so this sort of allows you to sort of capture all those Galois representations at once. Each of the TFs is now a quotient of this TM. But what I want to do is take the quotient of this thing by the Eisenstein ideal, which is now going to be something like finite. So let's set T to be T mod I T chi, I guess we'll take the chi part. So this is a module for both for the Hecke algebra mod the Eisenstein ideal and for Galois, which the actions commute. Okay. And in fact, it's unramified outside N and P. Okay. So let me explain this. If this is a little technical, let me explain this in the case N equal P. In this case, you know, chi is, let's say, omega to the k minus 2, and omega is like z mod p z. It's just an injection of z mod p z cross into zp cross by lifting a p minus first root of unity. Okay, so so I'm now viewing omega. Originally, chi was a complex valued character, but of course it was algebraic, and we've injected qr into qp, so we can make sense of this. And so then the theorem from I think 1932 and 1976 of Herbrand and Ribet, I guess Ribet recently won the Steele Prize for this result. So P divides this Bernoulli number if and only if the class number of Q mu P, so the class group of Q mu P, the P part, or the class number, or yeah, the P part of this class group in the sort of part on which Galois acts through the 1 minus k or P minus kth power of this character omega is non-zero. Okay. So the direction that class group implies P divides a Bernoulli number is kind of a simple consequence of Stickelberger's theorem, but the other direction is quite deep. And it was sort of the first connection. The way Ribet proved it was by looking exactly at the Galois representation of a cusp form that's congruent to an Eisenstein series mod P. Okay, and so what he did was Ribet. So we have this representation attached to choose a cusp form congruent to an Eisenstein series, G2 chi omega to the k minus 2, and he made a good choice of lattice LF of GQ stable lattice in our Galois representation VF, and then reduced it mod P. Okay, so when he reduced it mod P, so if you imagine Galois acting in some way on this lattice, he chose it in such a way that maybe I could try to write, right? So you have some Galois representation, right? Let's say rho F on the lattice, and maybe it's given by 4 maps, which you call A, B, C, and D, okay? And now we're going to reduce it, right? Rho f mod p is going to be, say, A bar, B bar, C bar, and D bar. But the way he chose this lattice is, and this depends on the way you choose the lattice, and this is the point, yeah, okay. The way he chose the lattice is chosen such that C bar is 0, which forces like one of, maybe it's, let me see, I forget, I might get this wrong, but let's say A bar is 1 and D bar is like omega to the k minus 1. Okay, and so what he got is, it looks like this, 1 omega to the k minus 1 and B bar. And moreover, he was able to choose it such that B bar is, or the rho f is lower triangular on inertia at P. It's unramified at, and it's unramified outside P. Okay, so now as soon as you restrict this thing to the Galois group of GQP, the omega becomes non-trivial, and you can see now you just have a homomorphism, this B bar. And so B bar defines a homomorphism from some Galois group of some K over QP to, let's say, FP bar, or maybe some number of copies of FP bar, but let's just say FP bar, where this is sort of a abelian, and K over Q is Galois, and a Galois element, let's say it's delta in Gal, so delta in Gal Q mu P over Q will now act, and you can ask, what is like B bar of, or like if I have how in Gal K Q mu P. So I lift my delta to some element of Gal K over Q. And the way it acts on tau is it raises it to the omega delta to the 1 minus k power. And so now, oh yeah, and this is also unramified. Maybe that's the key point, right? It's unramified because rho f is lower triangular on inertia. So, okay, but now we know by class field theory, this gives, and yeah, oops. This gives B bar from exactly this group we're interested in, class Q mu P, tensor ZP, omega to the 1 minus K, to, or maybe it was a subscript, to FB bar. And now I should make the point, okay? The other way this was chosen is that this is non-zero, right? The lattice can be chosen always to make it non-zero, and that's sort of a key point. He chooses the lattice to be extremal in a certain sense. You have like a rank 2 thing. You try to make one piece as, you fix one of the rank 1 pieces, and you make the other one sort of as small as possible. And in that way, you can sort of make this character non-zero, this B bar. And so you get a non-trivial homomorphism from this class group to FP, and so therefore you have the theorem of Rivet. But now the point I want to make is there's another lattice, right? This is not the same lattice as I was talking about earlier, right? I just took the lattice up here, over here, which is the quotient of the canonical lattice that comes from cohomology by this, or actually it wasn't here. Yeah. Yeah, that was the one. By the one that comes from the one that comes from cohomology, right? The canonical, it's sort of a canonical lattice. And essentially a conjecture of mine, so the canonical lattice can also be used, so TF can also be used to produce an unramified cocycle. But may be 0 a priori, because we haven't chosen it to be extremal. in any way. So conjecture of mine, which I'm going to discuss shortly, implies that in fact, these two lattices are the same. So, so let me go back to the general setting, but not
Sorry,
quite
Romyar,
fully.
can I
Yeah.
just ask a quick question? When you say
Yeah.
they're the same, do you mean as like as Galois modules or as like with what?
Yeah, they're literally the same. They're the same lattice inside the Galois representation VF. Well,
Thanks.
okay. I mean, yeah, what do I mean? I didn't say how Ribbit made the choice. So, there are many choices of lattice because you could always scale, right? But in this idea that you sort of fix one piece of the lattice to come from homology and then you vary the other piece. So the question is whether this TF is a lattice which is sort of extremal, or I think Wiles would call it mu deprived, in a certain sense, and that LF has to be to give this like sort of cocycle that you want, or this character that you want, this B bar being non-zero. And the answer is it is. You can use it to do this. Does that make sense? Like
Yeah,
they're both lattices in BF. So yeah. Okay, so P divides N. P is at least 5, and maybe chi is not omega inverse on GQP. Okay. Or chi, yeah, I think viewed as, mapping to like Z mod PZ. Oh,
Can I ask a question,
yeah,
Romyar?
yeah.
Um, do you have some? I think in general, this TF could have rank greater than 2 over ZP, right? So with the lattice that Ribbit
Right,
used
over
always
ZP.
has rank 2, or over OF, I mean, sorry.
Could it?
'Cause isn't the rank of this TF like usually something like 1 plus the number of generators of the space of cusp forms? Um, if,
I think not the TF, but the T could have rank greater than 2. But I think TF is just for one cusp form, right? Yeah,
okay,
yeah. But I think
okay,
T, which encapsulates sort of, or does T localized at M could have, yeah, that higher dimension. That's right.
I see.
Yeah,
Okay, thanks.
right. So basically, yeah, let me just, this might not be quite right, but I wanted the representation to be residually distinguishable. There'll be two characters, and I want them to be different uh, on the decomposition group at P. Okay, so Fukai and Kato, following some work of mine, uh, showed that T fits into an exact sequence like this. Okay, and so in fact, this is a picture of what I drew above. In fact, if you take the reduction modulus lattice and you look at this like C bar, it's actually 0 in this case. But that doesn't mean B bar is non-zero. So okay, so we have canonical isomorphisms as Hecke modules. P is cusp forms mod the Eisenstein ideal. But another way that's more useful for this talk of saying this is it's the homology of x1 of n, take part fixed by complex conjugation, then reduce that mod Eisenstein ideal, which I'll write this way because I want chi part. And Q is just as a Hecke module is just like H mod I. So it's like free of rank 1 over H mod I. And this has trivial Galois action. And here, GQ acts as omega, or maybe chi cyclotomic times chi, the cyclotomic character times chi. Okay, and now the key point is the sequence. This is of H mod I GQ modules. Sequence is locally split at all. all L dividing N. Okay, so just from the fact that you have an exact sequence, and this one's sort of free of rank 1, and I should say these isomorphisms are canonical isomorphisms. They're not just isomorphisms. Like there's a canonical generator of this Q. And actually the entire game here is sort of constructing this quotient Q with a canonical generator for what I want to do. So this gives us a cocycle. Because we have an extension class, it gives us a cocycle, GQ, for homomorphisms from Q to P. Okay, but now Q has a canonical generator, so we can just evaluate that. Now that changes the Galois action on P. So now, Galois acts as like the inverse of the action on Q. So chi cyclotomic, chi inverse. But we get this cocycle, and now the question is it non-zero? So its restriction to GQ mu n is now unramified, kind of, to unramified homomorphism. You actually have to go up all the way up to the P cyclotomic tower, so that's kind of inconvenient. But okay, restricts to an unramified homomorphism on this group. Okay, but more precisely, it gives us a map upsilon from, some H2. Because if you don't like tau cohomology, this is the Galois cohomology of the Galois group of the maximal unramified outside P extension of Q mu n with ZP2 coefficients. In the chi part in which Galois acts by chi inverse, and then it goes to this H1, this P. I'll just write, I'll omit the C for lack of space here. I'll just write it like this. Okay, so we get this homomorphism. So this is something that mod P looks like the part of the class group we're interested in. So the left-hand side mod P can be related to the class group of Q mu n in the chi omega inverse eigenspace. Canonically, it's also a group called K2. It's K2 Z mu n tensor ZP in the chi inverse eigenspace. K2 of this ring. And so my conjecture from 2011 is that this is an isomorphism. And Fukai and Kato have a big result on this conjecture, but actually on a more general version of this conjecture that says if a certain p-adic L function doesn't have a multiple 0, then this is true. I want to point out that actually I was recently sent the preprints of actually a paper, but there was a gap in another paper in a non-vanishing result of HIDAs for certain L values, which Ota recently sent me maybe like 3 nights ago, preprint correcting. So this says that if chi restricted to Z mod PZ cross, assuming n divides P, has non-trivial kernel, sort of a strange condition, then epsilon is an isomorphism. Okay, and that this epsilon being an isomorphism tells you that the two lattices are the same, basically. That this T is a mu deprived lattice is what he actually proves. Okay, so in the last few minutes, last 15 minutes, I guess, I want to discuss another side of this connection. Okay, so what is this H2 etal, right? It's also this K2. Either way of thinking of it, if the H2 receives cup products, the K2 receives something called Steinberg symbols, and they correspond on the two sides. And so maybe I should say I want to think about it in terms of K2 because that's something that's integral. So it already exists without tensoring with ZP. And what is K1? K1 is just the units in the ring. So this is what we call the group of n units in Q mu n. And the point is it contains very nice elements called cyclotomic n units, which are actually units if n is divisible by 2 distinct primes. 1 minus zeta n to the u, where u is a non-zero mod n, or u is an integer mod n. And so we get Steinberg symbols, which are the product in K-theory, which corresponds to the cup product in Galois cohomology. 1 minus zeta n u, 1 minus zeta n v, let's say, in this K2. Okay, and so the key point about Steinberg symbols is if x and 1 minus x happen to be units in this ring. Okay, so x is a unit, and then 1 minus x also happens to be a unit, which actually happens a lot for cyclotomic n units, but no reason to expect it to happen a lot in general. Then this symbol is 0. Okay, and that sort of puts relations among this on the Steinberg symbols of cyclotomic units. So in 2007, maybe I'll write this theorem. Buzyok and I independently, essentially, constructed a map from the homology relative to the cusps. So I need to, it's better if I don't take all cusps in a sense. So I'll tell you what cusps I'm taking in a second. To this K2. Okay, this K2 notice is slightly different. I inverted n, but okay. Oh yeah, I need to say something about what the symbols are. Okay, so here first, C1 naught n is the cusps on x1n that do not map to 0 on x naught of n, the quotient modular curve, where I don't impose a condition on D. Okay. The cusp is 0 in here. Okay. And here we have something called mon-n symbols. So I'll just write it here. Pi naught of u v, there's some symbol in the homology, and it gets sent to the Steinberg symbol. And we have some sort of, so here, where uv for uv in z mod nz minus 0 with GCD1 is a mon-n symbol. And the way you do this is you fit UV into a matrix ABCD in SL2Z in the sense that UV is the reduction of CD mod n. And then you consider the class of the, say, the geodesic. Doesn't really have to be, but so between minus, the way I normalized is minus D over Bn. There's a reason for this, minus A over Cn. And then you sort of minus, I hope I wrote it in the right order, but it doesn't really matter. So, right. So this gives you some class, and it gives you some homology class and homology relative to these cusps. So this is UV. And of course, if it goes to infinity, you draw a straight line to infinity. One of them is infinity. And so, so this pi naught actually restricts to a map pi just on the homology of the closed curve. It's just harder to, I should say, these mon-n symbols generate the closed homology, and they satisfy simple relations, which you can verify directly on, Steinberg's symbols of n units are satisfied. And then that's how you get the well-definedness of this map. And it restricts to a map just on the homology to K2 of the, there's a slightly smaller K2 group that we were considering before. Just differing by K1 of multiplicative groups of the the primes dividing n tensors EP. Okay. Notice this looks a lot like the map upsilon, except it's going in the opposite direction. And so I made a conjecture that, in fact, that pi naught is Eisenstein, which implies pi is Eisenstein. In other words, pi naught composed with t, or equals, or maybe pi naught of tx equals 0 for all t in the Eisenstein ideal and x in the homology. Okay, so in other words, yeah. Okay, so the theorem of Fukai and Kato I think it's really like 2011, 12, but just published 2024. It's true if if p divides n, which I guess I'm not assuming anymore. And then more recently published 2024 also. True for, maybe I should put it this way, true that T composed with TL minus 1 minus L diamond operator L equals 0 for all primes L not dividing n, which seems weaker, but we don't assume P divides n. And in fact, Lecoutre and Wang, so maybe this theorem, Lecoutre and Wang proved that this is all p is at least 5, but actually true, this is for p at least 5, and this one is not. P is at least 3 here. True for p greater than or equal to 5 and the map pi rather than pi circ, just by combining the two results and some level compatibilities. So okay, so assuming the conjecture, which is basically proven now, you get, in fact, it's proven for p greater than or equal to 5, which is the only case I've defined upsilon. So you get a map like this from mod the Eisenstein ideal to K2 Z mu n plus tensor ZP chi inverse. So notice this map is between the same two groups that upsilon is between, but just in the opposite direction. So here was my conjecture from 2011 that these two maps are inverse. So not only is upsilon an isomorphism, but it's inverse to this particular very explicit map between symbols. And then the theorem of Fukai and Kato is that, and maybe very slightly improved, but this is like minor compared to that by the three of us, is that it's true if, say, p divides n, p doesn't divide the Euler phi function of n, the same assumption on chi we had before, and the p-adic L function of, I need to get the right value. I think it's chi omega squared, but I might have that wrong. Chi omega squared has no multiple zeros. Or no multiple zero at, yeah, let's just say it has no multiple zeros. And this might be a bit of a not quite accurate, but okay. So great. And that's something that's expected to always hold, I should say. But we just have no idea how to prove that. So I want to go back to this Eisenstein property, and so since I said I want to talk about this with a view towards generalizations, so in the case of upsilon, to generalize this to some other setting, the key thing is to be able to construct this sort of quotient Q of the t. In this case, Fukai and Kato and my method with VaNTAGe are quite different. So what Fukai and Kato do is exploit the fact that you have Siegel units on the modular curve. And maybe I could just say that they both fit into the same picture. Because Y1n is a fine moduli space, it has a universal elliptic curve over it. Okay. And then we have this cusp here, which is spec of Z mu n 1 over n plus. And then over that, we have, well, we have like a nodal cubic, right? But let's say I just remove 0 from this universal elliptic curve. We have like GM here, or GM minus 1, I think. One or the other. Okay. But right. So what Fukai and Kato do is they look here. Okay. So on E minus like the C torsion points, you have a theta function. So maybe in the units here, theta C. Okay. And where C is say prime to C is prime to n, or prime to 6n. Okay, and this thing this has a unique section. So what is the fiber over a point in the universal elliptic curve? So the fiber over EP in E is E, okay? And there's a canonical map, canonical section here. Let me call this Sn. Sn of, or maybe Yoda n. Yoda n of EP is then the point P on the fiber E. Okay, and so you can pull this thing back by, if you pull this back by, let's say U times Yoda n, then you get what's called a Siegel unit on the modular curve. And this is some Siegel unit. And there's some way to modify this. You get some small denominators, but to remove the auxiliary C once you go to Siegel units. And what Fukai and Kato showed is that, you know, following, I guess there's also Gontran, Bruno in a slightly different direction, but, you know, there exists a zeta map, Z, from the homology of the modular curve relative to these non-zero cusps to the, okay, H2 of the modular curve. This is not quite accurate, but okay. Ordinary part. And they sends UV to the cup product of G U over N and G V over N. Okay, this is not quite accurate the way it's written, but the key point is what Fukai and Kato did that, you know, sort of Bruno didn't, is that this is and is Hecke equivariant. And so now the point is that when you pull this thing back by the cusp at infinity, okay, which you can do, so that'll give you a map to K2 H2 tau x Z mu n whatever 1 over n, let's say. What you get is actually the cup product of the two cyclotomic units. Okay, and then the point is that this is Eisenstein, as I kind of described before. It's annihilated by the Eisenstein ideal. So the composition of the two maps, a Hecke equivariant map and a Hecke equivariant map, which factors through the quotient of the Eisenstein by the Eisenstein ideal, is Eisenstein. So that's their approach. So it goes sort of this way, if you like. But you can also imagine going this way, or just going here. Really what they're doing is they're not even using the universal elliptic curve. They're just using the modular curve. And so that's what Akshay and I do. So the point is that we construct, so I'll end with this, a motivic cocycle, or an Eisenstein cocycle, from GL2Z to K2 of the function field of GM squared. So we think of GL2Z as acting on points of GM squared on the right, for instance, and then we can pull this back by, so here we have a section which is like 1 comma zeta, here we'll do GM squared now. So we have a section just for GM, which is like zeta n. And pull back by 1 comma zeta n squared. There's a way to make sense of this when I, upon restriction to, doesn't make sense now, but to gamma naught of n, and this gives us a cocycle gamma naught n. Oh, and this is Eisenstein in a particular sense. So gives us a map like this, which is Eisenstein away from the level for the TLs, L not defining n. And this gives us our map epsilon upon restriction to pi, restriction to gamma 1n. Okay. And so, yeah, so it's like a totally different approach, but you can see that they're linked through this picture I drew. And the nice thing about this motivic cocycle is it gives you the possibility of constructing maps in other settings, right? So for instance, I posted on arXiv, I think it appeared last night, a paper constructing such a map and showing its Eisenstein away from the level for Bianchi spaces and K2 array class groups of imaginary quadratic fields, where the idea should be, although it's not done explicitly in there, is that sort of symbol on Bianchi space goes to Steinberg symbol of elliptic units, which can't really be done explicitly, as I was saying, because we don't have any obvious relations like Steinberg relations among the elliptic units. Okay, thanks.
Thanks, Romyar. That was wonderful. Well, this is a great time for questions. Would anyone like to ask any questions?
Ask, does anything interesting happen at 3? I noticed that some of your theorems applied at 3 and some didn't.
Right, they should all apply to 3. It's not really that it's interesting, it's that you know, Hita has some additional complications when P is 3, which, you know, can be overcome. But Ota's work, which is used a lot in what Fukai and Kato did, they proved like lambda, there's some sort of lambdatic Eichler-Shimura and various other things that Ota did, was only done for P at least 5. And so, you know, one of my students kind of wrote this P = 3 case in his thesis, but I feel like it hasn't been published, so yeah.
Oh, so but you would expect your first conjecture? Do you expect it's true at P = 3?
Yeah, I think P = 3 is fine. P = 2 is a problem. But I should say in what, oh yeah, yeah, and what Venkatesh and I do also works for, well, I mean, it's, okay, this is kind of not quite true. I need to invert 2 in what I'm saying, you know, at the end there in the work with Venkatesh, but it works fine for 3. Yeah.
Thank you.
Well, great. Let's thank Romyar again. And our next talk will be on May 13th.